Okay, so let's look at some results for this uniform load camber line. What I did is I took a NACA 2412 and I put it into a panel code with 200 nodes, so 199 control points. And I put that at 0 degrees angle of attack. And that gave me a lift coefficient of about 0.259. Now, one thing that I forgot to point out about this uniform load distribution is that this lift coefficient here is what they call a design lift coefficient. So basically, we have to know what lift coefficient we want to produce at 0 degrees angle of attack in order to create this camber line. So then I put this camber line into a panel code, and I did a 12% thick camber line. So just like we had for the 24%, or excuse me, for thickness distribution, just like we had for the 2412, that was the same percent thickness. So I did a 12% thick airfoil using the uniform load camber line. Now, one thing to note is that I actually used a slightly different NACA 4-digit series in order to, or definition for thickness in order to close the camber line. And I've covered that in previous lectures, but the numbers that I used, I'll just show you here really quickly. The thickness is equal to the maximum thickness times 2.980 square root of x over c minus 1.320 x over c minus 3.286 x over c squared plus 2.441 x over c cubed and minus 0.815 x over c to the fourth. Okay, so this is an alternate thickness distribution that closes the trailing edge. This is a distribution that a student of mine and I came up with after running a bunch of simulations and trying to come up with a thickness distribution that matched the aerodynamic performance of the 4-digit series, but had a closed trailing edge. Remember, the original 4-digit series does not have a closed trailing edge. And so the panel codes tend to give better results near the trailing edge if you have a closed trailing edge. And so this is the thickness distribution that we came up with. So anyway, that's just a note that this is the thickness distribution that I'm using. And when I did that with this 12% thickness with the panel code, I did the panel code with 200 notes and still alpha equals 0. And this gave me a lift coefficient of 0.283. So notice that, and by the way, I put in this as my design lift coefficient for the uniform load. So that went into this setup here for the uniform load. That's my design lift coefficient. I was trying to match the performance of the 2412. So notice that when I come out, I get a lift coefficient of 0.283. So that's a bit higher than my design lift coefficient. And the reason for that is because we've used a camber line development here. This equation came from thin airfoil theory. So it was assuming an infinitely thin airfoil. So if I go back in and do a 1% thick airfoil, and I still use a panel code with 200 nodes and an angle of attack of 0, that gives me a lift coefficient of 0.258. So this is 1% thick and a uniform load again. So both of these are uniform load distributions. Again, I put in this as my design lift coefficient right here. And then if I have a 12% thick airfoil, I get a higher lift coefficient because remember our algorithm here is not accounting for thickness. So if I shrink that down and go to a 1% thickness, I get a lot closer to 0.258 at 0 degrees angle of attack for this uniform load camber line. Okay, so let's look at what these pressure distributions look like. The purpose, the reason we did this was so we could get a uniform load across the airfoil, and in other words, we wanted a pressure delta that was somewhat uniform across the airfoil. So what I have here is the NACA. Let's see, I'll even put this in the right colors here. So the orange is the NACA 4-digit. Actually, it's the 2412. And then the blue is the uniform load with a 12% thickness. So I call that a UL 12 usually. So in my code, I have a UL 12 instead of a NACA 2412. But anyway, so it's a uniform load, 12% thickness. And you can see that the variation or the difference between those airfoils is pretty small. If these weren't right on top of each other, you probably couldn't even tell that there was a difference in the two airfoils. But here's our pressure distribution for the two. So again, the orange is the 2412 airfoil, and then the blue is the uniform load distribution. And you can see if you were to walk along the distance and look at the delta in pressure from the top to the bottom, the difference between the two blue lines is very consistent, especially compared to the 2412. So for just a small change in geometry, which these thickness distributions are the same, it's actually a small change in the camber line here. You can see that we can have this control over the pressure distribution and create this uniform load distribution.